Okay, so my name is Shawn Beaulieu, and I'm a master's student at the University of Vermont. And the title of my talk is Combating Catastrophic Forgetting with Developmental Compression, which was created by myself, my colleague Sam Kriegman, and my advisor Josh Bongar. So my talk today is going to consist of a series of geometrical arguments that try to communicate the meaning of various approaches to obviating catastrophic forgetting, as well as introducing our method and distinguishing it from existing approaches. So let's say you have a problem that you want to solve, and the fitness landscape for this problem is fairly difficult to navigate. So here we have a situation in which only one configuration in our design space, that is the space of possible weights in our network, will obtain a positive fitness. Every other configuration will receive a fitness of 0. So in other words, a configuration that is as different as possible from the optimal value obtains the same fitness as one that is just a single bit different from the optimum. And because of this, there is no gradient for evolution to follow. However, if we move away from a situation in which we're exploring this design space discretely with static configurations to one in which we allow individuals to change over their lifetime, we introduce the possibility of passing through this needle at some point in the life of some individuals. So this was presented originally by Hinton and Nolan in 1987, in which they had a population of individuals that could change themselves by virtue of some function, which here was just random change. And in doing so, they were able to pass through some needle, the only correct answer in their test environment, and hit the correct configuration. Now, because there's a cost to changing oneself or for one's life, there's an implicit pressure to remove learning from the equation. So what this looks like is that descendants of this individual will obtain increasingly efficient paths toward this needle in the haystack. And the starting weights will change as well, until eventually we obtain one individual that has the correct configuration at the outset. It doesn't require any learning or any change whatsoever. So this is Kennelization. It's canalized around this single optimum. So this is applied to a single task, single very challenging task with only one correct solution. But what if we wanted to extend Hinton and Nolan to multiple environments? So we don't just want an individual that's good at task A or task B. We want an individual that's good at both tasks. But in moving to this multitask paradigm, we encounter a new host of problems. Among them is catastrophic forgetting, for which there's at least 2 formulations. One is a sequential kind of forgetting, in which if you introduce tasks in a sequential manner to an agent, tasks that are encountered earlier in the sequence will undergo performance degradation as new tasks are introduced. So you train on task A, then you train on task B, and in doing so, you've lost the information about how to perform task A well. There's another kind of formulation, which is antagonistic forgetting. And here, the tasks compete for representation in the system. They compete for system resources. So if you improve on one task, you necessarily degrade performance in the other. So what this might look like in a problem like phototaxis, where high fitness is obtained by close proximity to this light source, is something like this. So this agent is trying to get to this light source. This is its native environment. It's doing some kind of strange walk here towards this light source, non-optimal walk. But then if we take this individual and we put it in another task environment, which is defined by just a different location of the light source, it does exactly what it did in the previous environment. So it's not sensitive to environmental context. It doesn't change its behavior depending on new sensory information. So this is a specialist agent, and this is not what we're looking for. Instead, we want an agent that is good in both environments. It's proficient in both A and B. So as another example, the needle in this case, in contrast to Hinton and Nolan, is not high performance on one very challenging task. It is a generalist configuration for both tasks. So again, in the same kind of context, what this might look like for phototaxis is something like this. This agent has what seems like at first a non-optimal gait. It walks off to the left. It's gathering information about its environment. And then, after it's done that, it has discovered what it's supposed to do, what's required of it, and it walks in the appropriate direction. The same thing happens in environment 2. It moves off to the left, it gathers some information, and then it walks toward the light source, which is now behind it. All right. So there are a number of approaches to obviating catastrophic forgetting. A fairly recent one that has become popular is called elastic weight consolidation. And heuristically, what's happening here is they will train an agent on one task, and they'll try to identify weights that are important for that task. And then when they move on to another task, they will prevent those weights that are important from changing too much. So they'll add a regularization penalty to the loss function. And this restricts the system to a particular band of design. So this is good for preventing catastrophic forgetting on one task. So if you go back to the task that weight 1 was determined to be important for, you won't see a massive degradation in performance, but by constraining the system, you're potentially limiting it and preventing it from getting this needle in the haystack, this generalist configuration that is good at all tasks. Okay. So it seems like maybe a priori we should be able to use Hinton and Nolan in this situation. We have a single optimal configuration, a needle in the haystack. We have agents that can change over their lifetime. Why can't we just deploy Hinton and Nolan, hit this needle by randomly changing configurations, and then progressively oralify behaviors that occur late in the life of the individual? The problem is that now that we've moved to a multitask paradigm, we have a heterogeneous fitness landscape. So instead of this needle being surrounded by a sea of zeros, we have many local optima. And in this kind of environment, the system has no real way of determining what's the global optimum and what's a local optimum. Unless you can exhaustively search this space, which is infeasible, or you know in advance what a generalist behavior looks like ethologically, you can't tell if you've hit the needle or not. However, if you can get some agreement, you can increase your confidence that you've hit some local or some global optimum or something like it. So what this would look like is that for every task environment, for every trajectory you'd have them all converging on some common location. You have Baldwinification around some common point. But given that these trajectories are random in Hinton and Nolan, this doesn't seem to be very likely. You're hoping to get convergence on all task trajectories due to random change over the lifetime of the individual. So this seems a very unlikely scenario. So some modern updates to Hinton and Nolan have been proposed, one of which was presented here at GECCO by Crisantha Fernando. And here evolution acts on two parameters, the starting weights of the system and some parameter that governs local update rules. And for each task environment, the configuration is updated according to the particularities of that task environment. So here we have two tasks. We have a blue trajectory and a pink trajectory. But if we mutate alpha, which is what evolution is going to do, we change both trajectories. So these are now correlated, they're coupled. The change to alpha changes both learning trajectories. This can lead to some unfortunate conclusions. So what we want here is to decouple these trajectories. We don't want a change in the pink line to change the blue line, because before we have this pink line hitting the needle in the haystack, we don't want to corrupt that beneficial mutation. So what this might look like is something like this. So we have some linear change in the starting configuration. We hit one of these trajectories with mutation, and it doesn't affect the pink line. See, we're moving this blue line, not moving the pink line. And because there's also an added cost to housing multiple disjoint patterns of change, there's an implicit pressure to compress these, just like there is for regular Hinton and Nolan Baldwinian evolution. So that over time, these trajectories will converge on the same common point and Baldwinify around this global optimum. Okay. So the way that we implemented this for our paper is we had a population of individuals, each of which was equipped with what we're calling a genetic tensor. This is a collection of weight matrices that connect motor neurons and sensor neurons. It has a base matrix for that it uses in every environment, and then a task-specific weight matrix that serves as a target for the base. And then in simulation, the agent changes in a linear fashion, a simple linear fashion, as you can see in this top right figure, from the base weight to the target weight. So there's just simple linear interpolation between starting value and end value. Okay. And for our experimental setup, we have three conditions that we're testing developmental compression against. First one is just the developmental compression itself. So we have 30 evolutionary runs with a population size of 200. And what we're doing here is we're evaluating each individual in our population several times. The first, for two tasks, for example, is a non-developmental evaluation. So going back to that genetic tensor, we have a base matrix. We're going to drop each individual into task one and evaluate them non-developmentally. These are static evaluations. Then we go to task two, same base matrix, we evaluate them, and we obtain some fitness back. Now we go back to task one, and we have our developmental evaluation. linear interpolation between the base state from before and the target state for this task. Then we go over to task 2, same thing, linear interpolation, same common starting weight, a different developmental trajectory. The control condition, again, 30 evolutionary runs. It's a simple genetic algorithm. Here we're just turning off development. We're not using linear interpolation at all. We just have the starting matrices, and we're evaluating in both tasks 1 and 2. And then finally, we have a random treatment. And this is just the control treatment with heredity removed. So again, tasks 1 and 2, we're evaluating just static weight matrices. So let's take a look at performance here. So this is for the case of 2 task environments. This is the best performance for run champions across 1,500 generations. So for the control and the random, we're evaluating for 1,500 generations, and the experiments, we're evaluating for 750. Because again, we have 2 evaluations per environment, so we have to do half the number of evaluations for fairness of comparison. So naively, we might think that the control here is massively outperforming the experimental treatment and the random treatment because it's obtained such a massive fitness. Although we do see some marginal improvements in experiment and random. But if we look at the worst environment, we see that problem that we saw earlier with the videos. We see catastrophic forgetting. We see a massive degradation in the control in its worst environment. So this is the median minimum fitness across those 30 evolutionary runs. And in contrast, our experimental condition is able to avoid catastrophic forgetting. So it's not undergoing the same massive performance degradation that the control and random are, but it's not necessarily improving in the way that it did in its best environment. It's just merely avoiding forgetting. If we look at the beginning, we see the beginning of evolution, first 75 generations or so, there is some improvement in the worst task, which is encouraging. Maybe this is something that we can look more closely at and deploy more complex learning algorithms for, maybe something better than linear versats development for future approaches. Okay, so just to summarize, we have developmental change, which can be adaptive. So changing your configuration over your lifetime can allow you to discover some beneficial behavioral trait. And then because of the cost of learning, this can be progressively made to happen earlier in the lifetime of the individual. So you're canalizing around some good configuration. However, Hinton and Nolan, this formulation in 1, is not suited for heterogeneous landscapes, which is what we see for a multitask paradigm. We don't really know when we fit the needle, so we have to have some convergence. So the way we do this is we change the way individuals change over their lifetime. And we do this through modular development. So in contrast to Chrysantha Fernandez's paper, where there is a correlated or coupled change in the local task environment, we have decorrelated, decoupled change, where one mutation to a trajectory doesn't affect the others. And then we have this implicit pressure to compress our learning trajectories. Okay. And then for future directions, we hope to complexify development, use more complex learning rules or developmental programs. We want to scale this to more difficult and disparate problems, something different than just phototaxis, and also hopefully to synergize it with existing methods like developmental compression, or maybe expanding on Fernandez's paper and allowing for different sets of parameters, learning parameters for different tasks, and hopefully get this kind of convergence that we see here. Thank you.
Plenty of time.
Yeah.
So what's the most number of tasks you try this on?
Most number of tasks?
Yeah.
4.
4 tasks.
Yep.
And none of them experiencing.
Yeah, so there's this slide, the median minimum fitness. We saw that there is a kind of plateauing that happens for more environments, but it's worse than this, so we don't get this initial boost in performance. It's more difficult to avoid catastrophic forgetting. We also have a slide that shows or measures compression between base states and target states to try to see how well we're converging on a common point. And we see that compression is more difficult as we scale up to more environments, which you might expect.
So, would you see this method being applied with like plastic neural networks?
Yeah. So I tried implementing this with Hebbian learning, and I didn't really see any market improvements over linear development. They could just be the way we're formulating the problem. For example, I guess I don't have it. We evaluate individuals twice per environment. So maybe we can devise a scenario in which we don't have to do that. Maybe that's a limitation that's preventing Hebbian learning from getting the kind of improvements you'd expect for more complex algorithm. Yeah.
So what are you trying to ultimately apply this to? Do you think? What would you use this for? What's your long-term goal?
Yeah, so long-term goal is to get this to work for tasks that are much more different than phototaxis on light sources in different locations. So to get a generalist configuration for maybe the Atari game environment or something like the DeepMind environment, something like that we can confidently say is obtaining a generalist configuration for very complex tasks.
That's interesting. Yeah. So just one strategy for all of them?
Not one strategy, maybe a single network for, and maybe it wouldn't apply to all of these tasks, but the ones that are more common to each other, maybe we can obtain a generalist configuration, neural network configuration that can maybe form multiple similar classes of tasks.
Nice. Yeah. Okay, I think it was a quick talk.
Yeah.
Very interesting. Thank you.